Hello, welcome to video 13 in the lecture Advanced Mathematic Modeling. In the last video I showed you how probability densities transform when the variable is transformed y equals f of x. The main idea was that the probability of an event is invariant under the transformation, and then we obtain this formula. And if our function is invertible, we can solve this for q of y. And now, basically with this, there are two important applications, or two questions that can be asked. Make this a bit larger. The two questions that can be asked are either, maybe this we call this problem 1, or it's expressed like this. We have given our function f, and then we ask what is our transformed distribution y. And the second question is the inverse question. Let's say we know already our distribution y that we want to have. Given our q of y, what is our function f of x? Why would this question be important? This question helps us to understand or to draw random numbers from a certain distribution. Because let's say we can generate, we have already the distribution for p of x, and now I want to have random numbers from a certain distribution, whatever, q of y. For example, we will show later example, I want here to have an exponential distributed random number. And then the question is, I have this distribution already. What is the variable transform that I need to transform from this to this? And so I show how to solve the problem 2, and then later I give an example for this problem 1. So let's start with problem 2. And for this we start with the special case that p of x equals 1. So we assume that x is a uniformly distributed random number between 0 and 1. Why should we use this case? Because we want to solve problem 2. And so most random number generators that you find in mathematical libraries or numerical libraries, they give you random uniformly distributed random number. That was just the command rand. And so now the question is, so we get our random numbers from the computer. What variable transform do we need to obtain our desired distribution? So this case that p of x is a uniform distribution is important because that's the distributed numbers we get typically from the computers. But now we see that in this case our variable transform is very simple, because then, or it simplifies, because this p of x equals 1, and we have a more simplified formula. In this case we can write down our q of y is just the derivative dy over dx, because this p of x is constant. And now this q of y is now the distribution we want to have, for example, an exponential distribution. And our question is, which variable transform between y and x yields this distribution? Now in order to obtain this, we just solve this for x. So we multiply both equations, both sides, by dy and integrate. Then we find that x is given as the integral q of y prime vy prime, and we integrate from 0 to y. And so then we have solved this solved this for x. But this here is nothing else than the cumulative distribution. This is our q smaller of y. And now the cumulative distribution is a monotonous function which can always be inverted. And so we can invert this. And then we see our y of x. This is the inverse function of our cumulative distribution of x. And this is what we were looking for, because this is the variable transform from variable x to variable y, which gives us our desired distribution. So we see our desired variable transform is just the inverse of the cumulative distribution. And this is something to remember. And we can also get a bit better intuitive understanding for this, and we can learn something here. In general, that goes beyond the application to generate random numbers. Let's say we have here our continuous variable transform, our continuous probability density, Q of y. And let's here also over y make a sketch of our cumulative distribution. Q smaller of y, which ranges between 0 and 1. And this is here an increasing function. So that's our cumulative distribution. And now, so what does this theorem here say? So what random numbers, what random variables x do we need to obtain our Q of y? So basically it means the x are uniformly distributed, so we just take a random variable uniformly between 0 and 1. Yeah. Q of y equals x, so that's x, that's uniformly distributed. We take any such value, we go make the inverse of the cumulative distribution, and then I find the x value which corresponds to this. So I take a random number generator, I generate a random number between 0 and 1, and maybe this random number will be this value here. Then I look in my cumulative distribution and find this y value, and this is the y value that we were interested in. So that's graphically how you find the function which you need between the transform between two variables, so that the uniform distribution here is transformed to some general arbitrary distribution. And so what we also see, that all values of the cumulative distribution in general are uniformly distributed. All values of the cumulative distribution are uniformly distributed between 0 and 1. This is a general statement for continuous random variables. So that's also one of the advantages of the cumulative distribution. It has these nice properties. For example, every value here appears with equal probability. Okay, so now we have seen the algorithm. Let's use this to in a special example. And this example is the exponential distribution. Let's say we want to generate random numbers which are distributed by an exponential. So we want to have, let's write it, q of y equals a constant times e to minus parameter lambda y. The constant here I will plug in a moment. So this is a distribution, a density, which is just decaying from some value at 0, like an exponential. So we need here a negative, and lambda is a positive value, a positive parameter, so that this function is normalizable. So we need a negative function. And when you normalize this, so that the integral under the curve from 0 to infinity is 1, then you find that we need here lambda. And we want that y is a positive variable. And this is our q y, and it starts at value lambda. So then the integral over this is 1, and this is really a probability density. So this is one of the fundamental distributions. This is typically, and we will come to this later. Typical examples when you use this are waiting times. For example, the paradigmatic case is you have a radioactive atom, and you want to wait for the next decay, and so there in every time instance you have the same chance that something happens, and then the waiting time to the next event is exponentially distributed. So this the waiting time for something that happens with a constant rate. And if you replace time by space, then it's the typical space between certain points. For example, if you have a cloud, a gas of molecules with a certain constant density, and you want to know what's the typical distance to the next molecule, that's an exponential distribution here. So something like you have to wait a certain time, you go for a certain distance until something happens, and then the exponential distribution is quite cool. So what's the cumulative distribution of this? Or in one of the exercises, you will look a little bit at this. So you will see that the expectation value of y is 1 over lambda. So this 1 over lambda, so something like the half decay rate here is also the expectation value. And in this case, this is also the standard deviation of y. So the standard deviation in this case equals the expectation value. So the standard deviation is also 1 over lambda. And we can calculate the cumulative distribution of y, q smaller of y. This is just simple integral, and this is 1 minus e to minus lambda y. So this is an exponential which goes to 1. So here we have the PDF and here the cumulative distribution. And now the question is, we want now to apply all that what we learned here and want to see how can we, if we have an algorithm in the computer which gives us uniformly distributed random numbers, how can we generate an exponentially distributed random number? So now we ask generation of exponentially distributed random numbers. So, and now we use just the formulas that we have seen here. We can maybe best use this formula here. So x equals the cumulative distribution. I just wrote this down. So I told you in the exercise you will learn how to calculate this mean, deviation, cumulative distribution and properties of this exponential distribution. So for now I just take this. So that's the main variable transform. X is the cumulative distribution of our PDF. And now we have to find the inverse transformation. We have to solve it for y, because y is given by the inverse of this. So then y equals minus 1 over lambda times logarithm of 1 minus x. And this is the variable transform that we need. It's quite straightforward. So this means, what do? We take a uniformly distributed random number between 0 and 1, take 1 minus this, take the logarithm, multiply this minus 1 over lambda, and then we obtain, then we find random numbers y which are exponentially distributed. And now a small trick. If x is uniform between 0 and 1, then x bar equals 1 minus x. This variable is also uniformly distributed between 0 and 1. So it means in practice we take y equals minus 1 over lambda times logarithm of such an x prime, which is even more simple. So we generate a random number uniformly distributed between 0 and 1, take the logarithm, normalized by minus 1 over lambda, and then we have here our, oh Jesus, you didn't see it, sorry, here again. So we take a uniformly distributed random number between 0 and 1, take the logarithm, normalize with minus 1 over lambda, and then we have our exponentially distributed random number. And a similar way, so here I calculate this step by step for the exponential distribution, and actually so there was not much to do. I mean, what we have to do, we have to calculate the cumulative distribution, and then we just have here, and then we just have to invert it. That's all we need, and then we have our variable transform. Okay, so this was for how we solve the first question. How the second question, how, if we have a given probability, desired probability distribution, how can we calculate the function f of x? And in the next video we want to look for the other problem, what is a typical application that we have already a variable transform, how can we calculate the new distribution? Okay, for now, thank you.